Moyen, welcome everybody to our webinar. This is the last webinar of the series of webinars that we organized about high performance computing or HPC or supercomputing. By we, I mean Lux Innovation in partnership with LuxProvide and the University of Luxembourg. For those of you who don't know me yet, I'm Ramona Caulea and I work at Lux Innovation, the Luxembourg Innovation Agency. And today, here with me, there is Valentin Plugaru from LuxProvide. Valentin, would you like to briefly introduce yourself, please?
Yes, thank you very much, Ramona. Good morning, everyone. And again, thank you for joining this session. I'm Valentin Plugaru. I'm the Chief Technology Officer of LuxProvide, and I'm very much pleased to present to you a bit of what we are doing at LuxProvide and to talk about MeluXina, to go a bit deep into the technology side, but also the kind of applications that are running today on the machine.
Thank you, Valentin. So, I will introduce you a little bit to the platform from which we are streaming today. So we'd like this webinar to be as much interactive as possible, as always. So don't hesitate to introduce yourself in the chat. So you see on the right side of the screen, you have the chat. For introducing yourself, sharing your LinkedIn contacts, and for technical questions in case you don't hear us well or you have some issues. Then we have the questions box. This is the place where you are invited to type your questions on the content. We will have a Q&A session towards the end of the webinar, so we will we'll try to take all your questions to answer. Then we have also an anonymous poll, as usual, to understand to whom are we talking to and to see if we are responding to your needs. Let's see together the poll and the questions in the poll. The first one is, how did you hear about this webinar? Through social media, emailing, Lux Innovation website, or newsletter, or directly our emailing, other sources or press. Then we have a second question to test your knowledge about supercomputing in Luxembourg. Is how many supercomputers do we have in Luxembourg, in your opinion? In your knowledge, 1, 2, 3, or you don't know? And then last question, was this HPC Thursdays webinar series useful for you? Yes, no, or you still need to figure it out. We'll have another question coming up towards the end, but we'd really appreciate if you could answer these questions that we prepared for you. And while I leave you some time to answer, I'm going to the concept of HPC Thursdays. So basically, we wanted to bring to you the basics of the supercomputing world to let you understand which are the benefits of using high-performance computing for your activities, being either research or business or any kind of organization really could use supercomputing power to boost their innovation capabilities. Then we had a brief introduction on basics, basic components of supercomputers and how to use them efficiently. We had then a specific session on the simulations and one on artificial intelligence. Then we had more specific examples of HPC usage in different sectors, for instance, health, finance, digital history, and public administration. And today we have the presentation of MeluXina to understand the MeluXina specific features and how you could access it. I really invite you to see all the replays on Lux Innovation YouTube channel from the past session. I posted the link to the to the playlist in the chat in case you'd like to have a look at it. Well, given that our HPC, our webinars, HPC Thursday, are coming to an end, we thought about organizing an event that is taking place next week at the Chamber of Commerce. This is the Supercomputing Day in Luxembourg. So we'll have presentations from the EuroHPC joint undertaking. We'll have a keynote speaker coming from Germany, speaking about the developments and the future of HPC, and then we'll have a presentation of mapping about the main players in Luxembourg, and also about the trends in the supercomputing world. We'll have also first roundtable discussing partnerships and funding opportunities in Luxembourg, and a second roundtable where we have companies acting as testimonials that will present to you how they use supercomputing in their business. So and actually we have also networking sessions. So we'll have some drinks and the opportunity to speak to HPC experts such as Valentin, but also Mathieu, and other HPC experts from LuxProvide. So you have the opportunity to register. Registration is still open, so I'll be happy if you join us. Today, let's go to discover MeluXina, I would say, to see what Valentin will be presenting and how you can make and access and make the best use of supercomputing power we have here in Luxembourg. So I would leave the floor to Valentin for his presentation. Valentin, I now remove my slides and leave the floor to you to present your slides.
Thank you very much, Ramona. So good morning again, everyone. My slide deck should be appearing now.
Yes,
it's really a pleasure again to thank you, Ramona. It's really a pleasure to talk to you, to present MeluXina and LuxProvide. What I'm doing now should come not as a surprise to some of you that may have seen the previous sessions. This is the 8th in a very nice series that comes as an initiative from the EuroHPC Competence Center of Luxembourg. And there, my colleagues from LuxProvide, but also colleagues from the University of Luxembourg, presented quite a lot of use cases, presented what supercomputing is about. So I will test you a bit on this, and will ask that in the Q&A we exchange very interactively about what you still want to learn about, and things that you want to ask, because it's a good chance now to talk together. First of all, if some of you are coming to this series and you have not seen this kind of slides presentations from LuxProvide before, a quick introduction of LuxProvide. We have been created as Luxembourg's high-performance computing center. We're operating supercomputing and data infrastructure. In practice, this is the MeluXina supercomputer. We are having expert teams with a broad variety of skills that transcend pure HPC and go towards data. We have experts that know cloud and that can bridge the words of HPC, AI, data, and cloud together to bring good services in the direction of bringing in the Luxembourg ecosystem, but not only in Luxembourg and beyond, in the European ecosystem, excellence for innovation, for science and decision making. We are tackling all sectors of activity, from public research and public administration to industry. We are a hosting entity for the EuroHPC joint undertaking with the MeluXina supercomputer, and we are also part of the EuroHPC project. So on both of them, I will speak in a few slides. So first of all, for MeluXina, you have heard the name MeluXina quite a lot already, I'm sure. It's a part of a nice network of machines that Europe is building, that has been building, because some of them are already operational and more are coming. The idea is that supercomputing is truly an enabler for a variety of domains. It's the desire is for supercomputing to be an enabler and to underpin the digital strategy of Europe for the digital decade, to help boost the things that have been done before, and bring them to the next level, but also to bring new things that could not be done without this kind of infrastructure. Now, the infrastructure is just a part, so it's good that you have infrastructure, that we have infrastructure in Luxembourg and in Europe, but then you need expertise to pilot it. You need, of course, people that are able to operate such machines. They're highly complex. There's layers upon layers of hardware and software, and I'm sorry, but in this presentation I will talk quite a bit about the technology as well. But in the end, it's about expertise and taking use of this infrastructure. So within the scope of European projects, and in Luxembourg in particular, there is this competence center that forms a body of knowledge, and it's a single point of contact for all questions regarding supercomputing in Luxembourg. And then there we are partnering together with Lux Innovation University of Luxembourg to make things happen, and then we are leading some work that is tightly coupled with business development and collaboration with industry, which is a good target for us. We are organizing trainings and workshops dedicated to industry, to bring up the maturity and the skills in industry, and also, of course, to enable organizations that already know how to use HPC to take advantage of the nice machine that we have. Across the different countries that are part of EuroHPC, there's also coordination that is happening through a parallel project which is called Castiel. And then the full idea behind all of this is that we are bringing together the hardware, the software, and the people skills, and we are trying to grow the maturity of all organizations in Luxembourg and abroad to take advantage of this kind of facilities. So why do we do this? HPC experts do HPC because they like HPC. Other people that don't like HPC want to get something out of it. So this is a slide that we're showing quite a lot. For industry and science, in principle, it's about these three things that you see. You improve the time to market. You're doing a better thing than others are able to do because you're taking advantage of Formula One facilities. You're doing things to a larger scale than you were able to do before, either in terms of data or increased resolution if you're doing weather modeling, or you're doing better physics, better chemistry, you're using improved algorithms on larger amount of data that you cannot do with your laptop, you cannot do with a tiny machine under your desk. You can do it with a supercomputer, and that's what the supercomputer is for. And of course, there's the last point, which is quite important. Being able to save cost while doing this. So not only doing it by applying a huge amount of power, energy in terms of pure electricity, but also in terms of people time, but also to save cost by testing more configurations, by using modeling and simulation, rather than doing it in life with real trials, with physical trials. Of course, at society level, they don't care maybe about the science part, but then you care about optimizing the way we're already using things. So if we have the way we're using the natural resources that we have to be sustainable, and the existing products to use them in a better way. It's also about finding new ways of using the body of knowledge that we have today and the tools that are there in the direction of enhancing daily lives. And it's also about discovering new things that we know will lead to better future, to better products, to better knowledge, better methods. So supercomputing is really the superlative part of computing. It's about doing either things faster than you're able to do, building things smaller than you thought is possible to do, finding ways of doing things in a simpler way to bring less complexity where the complexity is something that is unmanageable, doing things in a better way to a larger scale than before, and also more complex things that we can imagine. So it's really a spectrum of things that can be done. So the next slides that I will show you present a bit of and hopefully you will get a bit of understanding of how this actually is done in practice. So if we want to talk about MeluXina in practice, so there was a vision behind the creation of MeluXina. So the vision was quite simply to serve a variety of workloads that correspond to the convergence of traditional high-performance computing, modeling, simulations, and data analytics, big data analytics, and artificial intelligence, to cover the key sectors of Luxembourg, which go from smart mobility to space, to help boost industrial competitivity, and to really see a lot of use cases that are covering as many domains as possible. So it was a nice challenge in the design of the system, but the design of the system was not only about the sectors, but also about practical use cases that people wanted to cover. So MeluXina was designed to help, for example, in the space domain, when you're designing satellites or space stations, where you want to launch satellites to see how the weather in space is going to look like. Are there things that will collide on a specific date in the place where you want to place your satellite? To analyze the data that the satellites are collecting, to do materials science to build better sensors on the satellites, or satellites that can last longer, or to do any kind of manufacturing in space. So all of these kind of use cases are tied to the space domain, and the supercomputer can help with them because you can do things to a larger scale or faster, which is enabling this use case. But space is one domain. For engineering, you can do digital twins, you can virtual test prototypes, you can simulate how a factory behaves, and do digital pilots. You can optimize production and manufacturing. If you're talking about finance, you can simulate risk and analysis, you can detect fraud, you can do simulations of the full economy, which is something that takes in a whole lot of data in the end, that runs complex equations, and that you are able now to do this in a way that was not really possible before, not only by the kind of infrastructure that is there, but also by the tooling and the expertise that can be brought to take advantage of it. So space, fintech, and manufacturing are important fields, but it's really not everything. So if we talk about mobility, you have a lot of logistics happening. I think over the past couple of years, we were all very happy to get packages delivered on time. So in the back, that's a lot of work on improving transport routes and stock warehouses, where to place them, how to bring them closer to solve the last mile problem between the huge truck that is coming and with all the packets inside and things that are really coming to your door. So there's a lot of things in this dimension that can be done. We all know that smart cars are something that we want for safety reasons, for comfort. So virtual testing of automated driving things are something that is done with computer vision. Supercomputers are really good at that. That all of this is tied to mobility. Healthcare and personalized medicine, I really should not need to introduce this, but we've seen with the COVID that this is pandemics do happen. They really happen during our lifetime, and it's quite a heavy thing. And then you need to have a response. So you need to trial things out. You have a lot of medicine that looks promising. How do you know that they will lead to something? You can do a lot of digital twins of the human body to see the response before you do your actual trials in live with real pills, with real people. So accelerated the drug discovery process, and also seeing how people will behave to it, and going down to the person level, so doing real personalized medicine, not only generic drugs that work statistically well on people. Climate and weather is really traditional use case for supercomputing, and I do have a better slide for that, so I will introduce it a bit later. So maybe the last thing that I will say is for smart cities, urban planning is something quite important. And there's a lot of things regarding, for example, weather modeling that ties into urban planning, because you know that there is a risk of flooding, and the urban planning needs to take this into account. And then you can do a lot of things that are coupling actually climate, not climate maybe, but really weather prediction and climate modeling as well, and urban planning together. So to design better houses and better materials, that's something that is happening as well in this direction. Now, MeluXina, from a technical point of view, was designed to be able to do all of these things. So in practice, the system has a few computational modules that are providing the bulk computational power, where you're able to run applications, real software that solve part of the problems that we've been talking about before. In practice, the MeluXina system is composed of a cluster module, which has CPU, a lot of computational units, and a lot of memory coupled with each of these units that enable a lot of tools to run, and all the tools that you could imagine can run on this kind of module. Most of the computational power of the system, however, is driven by the accelerator module. And this is the brick that is accelerated with GPUs, GPUs that can be used for accelerating computation. The idea there is that you have state-of-the-art GPUs inside the system. They help very well on data-driven workloads, but also they're really well at accelerating AI workloads, which in practice is machine learning and deep learning tools. Tied to these GPUs, we also have a small partition inside this module, which has really dedicated accelerators for specialized workloads, which are called FPGAs, or field programmable gate arrays. And they are highly custom. They will run in hardware the software program that you want to run. So you're designing the functions that you want to run, and then they're doing this in hardware, which is then faster than doing it in software. So all of these computational modules are tied together with a lot of storage. So there's a storage system in a backend in MeluXina, which is actually a series of data tiers, which are providing the capability to store huge data sets and programs, applications inside that run huge computational workloads well. And it's been designed also with a tiered approach, with a part that can be considered an accelerator for data analytics, and other parts that provide a lot of capacity and also a long-term storage that then help with the that help projects analyze their data and do a lot of processing during a project lifetime, which can sometimes last years. Coupled together the hardware for compute, the hardware for the storage, you of course need to come into the machine, so you need connectivity to the machine. So then we are connected with MeluXina to the national ecosystem with multiple differentiated links. So it doesn't matter if you're industry or if you're coming from public research and academia, you will have excellent connectivity to inside the machine to bring these data sets so that you can then process them well there. Of course, there's a system module that pilots all the computational and storage parts, all the logic behind the system, and there's a lot of things that we are doing to enable a very nice usage of the system through cloud facilities. The architecture of the system is one thing, but what does it mean in practice? So the sizing of it. All in all, we have around 1,600 CPUs that are really HPC oriented. They're high power, high density. There's 90,000 CPU cores. So if in your laptop you have around 4, maybe 8, maybe 16. You have 90,000 of them in MeluXina, and it's not only that they're there, but they're also closely coupled together with a topology that is enabling them to work very nicely together to bring the use cases to fruition in an efficient way. The CPUs part are present in all the computing nodes, the elements that are running the code, but you also have the accelerator part, which has different kind of tooling that can take advantage of it, and it can also, if you talk about AI cores, then there's more than a third of a million of AI cores inside the MeluXina system. The CPUs, the GPUs, the live memory, the storage, the topology is glued together for users through a complex software stack that enables you to use this kind of the hardware and the storage facilities. In terms of performance, the machine is called an 18 petaflops machine. It's been ranked as a 10 petaflop machine in a single execution benchmark, which allowed us to show that it's a truly world-class system. In terms of data capacity, the current storage capacity of the machine is around 25 petabytes across the different storage tiers. And the interconnect that is inside the machine is the very specialized high-performance computing interconnect, which is called the InfiniBand HDR, 200 gigabit per second for every single compute node inside the system. Also, the accelerated parts and the large memory parts that provide in-memory computing capabilities are coupled even with multiple links, such that you can really drive a lot of high bandwidth and low latency applications inside this environment. Regarding the system, when the system was first put to life, we ranked it across multiple tests to show that it's a world-class machine. We were able to show that MeluXina is arriving as the one of the world's top in terms of performance, but also is doing this in a very efficient way. And this is due to the nice European technology that is involved in the high power parts of the machine, the accelerated and the non-accelerated parts, which are liquid cooled. And at the time, more or less 1 year ago, we came up as the first machine in terms of energy efficiency that was able to reach this performance level of the 10 petaflops that the accelerators can give. Of course, purely the compute part is one aspect. In terms of I/O performance, data performance, and graph analytics, we were also quite highly ranked in the world rankings. But I think that's enough around the hardware parts. Let's talk a bit about the software. To bring the software to life, of course, you have a lot of tools that people want to use. Python is more or less quite heavily used in the past 5 years. C++, Fortran codes are also used quite a lot in various domains of science. So you have real applications that people want to use. You have libraries for data, for acceleration that people want to use. So if they come to the machine day one, they need to find something that is enabling them to be productive. So one thing that we did with our expert teams was to create a rich software environment that presents a lot of tools, open source and commercial tools from independent software vendors that enable all of those use cases that we talked about before. The true challenge is that the software moves at the speed of light, well, beyond speed of light, actually. So it's a true challenge to bring a software stack that is also production ready, that is stable, that works well, but that is also close to the recent versions that people want to use, because new software always has nice new features that you want to use. So those were the goals and the challenges that we had in front. And to bring you a bit of a sense of complexity of what this means, I will do a deep dive. It's a short deep dive into 3 types of tools. The first of which I want to talk about is GROMACS. It's a molecular dynamics tool. It's well known in the for life sciences, for chemistry, computational chemistry. It's used, for example, to design drugs, to design medicine, but not only. It really has a lot of application areas. The tool has tens to hundreds of dependencies, and it can do non-accelerated work, but it can also work with the GPU accelerators. And there's many ways to control the way this is used to run it in an optimal way. And every time, if you bring this and you want to run this tool on a supercomputer, you need to do an optimized build of it. You need to deploy it to take advantage of the architectural features of the machine. So then not only this tool, but also all of these dependencies are really built and really compiled and built with specific flags to take advantage of the hardware that is there. And this is something that we are doing, so that when a user comes into the platform, they will find many versions of GROMACS that are compiled with different kind of options that are making this efficient. And if you think this picture looks complex enough, I will introduce you to the next one, which is it's a pair of packages, TensorFlow and Horovod. They're used for scalable machine learning, deep learning, and AI. which have way more dependencies than GROMACS. And here, well, compared to GROMACS can run very well on CPU and can do a bit of GPU. Well, some parts of it can take advantage of the GPU. But TensorFlow and Horovod were from day one made to work very well with the GPU. So they can work on the CPU fine, but they're really meant to take advantage of the GPUs. Then again, optimized builds for the MeluXina architecture are essential, and we're doing this. They come with a ton more dependencies, and thankfully users of the platform don't have to do that on their own. So this is just to show a bit of what is behind this software stack. And to maybe the last element to show you on this is another kind of tool which is used for computational fluid dynamics, which is called OpenFOAM. It's really used across the automotive and aerospace fields, but not only. So if you have some pipes, some industrial facilities, it's quite likely that at some point some piece of it was designed with using maybe not OpenFOAM, but this kind of a package. But OpenFOAM is used across industry and science for designing new things. It comes with many dependencies, much more than the tools before. It links with a ton of solvers, a ton of software tools that are enabling it to do the work that you want to do. And this kind of tools and all of these dependencies, again, needs to be built on MeluXina to really take advantage of it. So the way we're doing this, the way we're building these tools is happening in a controlled way using a platform which is called EasyBuild. And it's being tested with another platform which is called the Reframe. And the idea is for us that every time you come into the machine, you find the software stack, you are able to bring your own tools, but then you can really benefit from the ones that have been built already by the teams here, because then they're really meant to provide you the best usage of the system. To give you a feeling for what the software stack comprises, so knowing that it's a difficult balancing act between all of these tools, their dependencies, the compilation flags, their options, the way they can interact nicely or badly with one another. There's still a lot of set of tools that go from basic things to build, so compilers, languages, tools to check how application is run, from different programming languages to different kind of compilers and different kind of performance tools, such as the ones from Intel, from NVIDIA, from ARM, open source tools like Scorpy, Valgrind, Papi, that are really enabling you, when you develop some tool or some model, to understand where the bottleneck is and how to go beyond it. That's just the basic brick that sits on the bottom of everything. But then people don't want to use that always, or don't need to use it always, because sometimes you don't want to develop your own tool to accelerate something. But there are a lot of libraries that enable you to take advantage of the GPU accelerators, for example, for doing fast Fourier transformers on the GPUs, or basic linear algebra. You have accelerated packages that enable you to do that, and you don't need to rewrite or to write your own or to rewrite things. And also tools for parallelization. So this is quite key for a supercomputer. It's what makes a supercomputer be able to do what it does. So you have a lot of different parallelization tools or parallel libraries that enable you to work with the system. Numerical and data libraries are really a must. A lot of tools, actually, if we would have been able to explore deeply the dependency tree of every single package of MeluXina, you would have seen that it comes in the end down to quite a few very intensely used tools that do, again, fast Fourier transform, that do linear algebra, that do that know how to manipulate different data structures, and to do it efficiently, and not only for that you are able to do that efficiently on a single compute node, but also across a supercomputer environment. So taking advantage of the parallelization capabilities there. On top of all of those prerequisites sit platform tools like frameworks such as TensorFlow, PyTorch, which don't do anything on their own. You need to program something against them, but then they're doing the heavy lifting of the neural network, deep neural network that you want to pilot through them. We also have some tools for quantum computing and quantum AI on MeluXina that is going to enable people to design the next generation supercomputers that will have quantum modules inside. And in the end, if you're a scientist and you don't care to program your own thing, but you want to use GROMACS, Quantum Espresso, Horovod, BioPython, or other tools like NWChem, you find these tools already on MeluXina. So in total, we have around, well, almost 400 tools in different versions. There's at least 300 tools, and among them you find quite a lot of applications that are commonly used within a supercomputer environment. For molecular dynamics, for computational fluid dynamics, for visualization, and for doing life sciences work. Of course, you do have an alternative to all of that. It may not be perfectly optimized, but you can control, as a user on such a system, you can control really deeply the kind of software stack that you bring and the pipeline that you run. Sometimes you need very specific versions for your own project, and these are compiled by you with your own specific tools. And you can do this in your own infrastructure and build a container, and you can run this kind of container on MeluXina, knowing that we're running the Singularity platform for that, which is compatible with Docker, so which is quite well used now for in many different industries and research directions across, well, for now more or less a decade. Singularity brings some nice features. If your application is GPU enabled, you can run a GPU enabled application through Singularity. It also supports running encrypted containers and running trusted containers that are signed and verified. And this means that if you're on the industry side and you have algorithms that you don't want anybody to look at, you can package them in a container and you can run them, and you're going to trust that this is only things that you know how it works, and that this is running in a trusted way on MeluXina. Finally, I think it's enough talk on the hardware software side. Maybe let's talk a bit about the applications that are running on MeluXina, not only on a conceptual point of view, but the things that we've really seen running on the platform in the past months. So the MeluXina system, since its inception, has run up until now a pilot program that ran for a few months. Also commercial projects and projects from the EuroHPC joint undertaking from universities and research centers across Europe. Focusing on things that happened through the pilot program, we've run applications that deal in the automotive sector. There's been work that deals with materials design for next generation vehicles, and where there is an optimization process that tries to be applied to improve, well, in one direction fuel economy and in the other direction safety. So to bring you a sense of understanding on this, it's if you try to build a next generation car, you may need to do many simulations around, for example, the tires that are running that are applied to the car, and the tires can be designed in many different ways. They can be subject to many different conditions. In the end, there's a lot of physics that are involved, and these physics are really complex equations that need to be solved. They take a lot amount of time. Sometimes you don't know what you're looking for, but you know when you'll find it. So the parametric studies that can happen to make this a reality really requires a lot of computational capabilities, and this is the kind of work that has been done and accelerated on MeluXina in the past months. In the direction of space usage on the space domains and space applications, you may have seen in the past days there's been a very nice communication around the joint project between SES and the University of Luxembourg SNT Interdisciplinary Center around optimization of communication systems and the satellite performance that deals with communication. But that's not all that you can do, and that's not all that has happened on MeluXina in the past months. Another type of work dealt with boosting the design process for engines that will go in for satellites, for rockets. And here the work is happening to bridge HPC and AI techniques and accelerate the simulation time for the design process. And this means that next generation machines, they may come in a few years or in a decade, but all of that work is being, well, the groundwork for it is being done today. Now, bringing things closer to Earth in the direction of agriculture applications, there's been organizations that ran whose goal is to really improve crops, to be able to see the yields that will be getting, to enable food planning, to improve food security, and how this is done. It can be done in very many different ways. You can use space sensor data. You can look at imagery and other type of information and detect where water is, to identify if crops grew well, to see the kind of patterns that you may have seen in the past, and to try to see, okay, this area will not have enough water, we need to breeding it artificially because the natural process this year will not happen to rain enough. So then if you understand this well enough in advance, you can do the true planning behind it, and then you can you're optimizing the process. We do have a globalization challenge to bring a completely different use case. So one thing that is quite funny, if you have not thought of it before, is the true challenge behind globalization and automated speech recognition. You're speaking with an Alexa or Google Home Assistant or with your phone, and sometimes you're using words from a native language, or you're talking with somebody, and sometimes you're intermixing words, or you're talking in a multi-language context, and somehow these AI assistants need to deal with that. So to be able to interpret the speech patterns, that's one thing, but then to recognize that one language has been spoken up until now, and now another language or a word from another language is being spoken, there's a thing that is called does a code change within the algorithms that are running that detect this thing, and to detect it well, it's quite complex. So you need to do a lot of simulations, not only for training on the data of how this can happen, but also the algorithms that are better are catching this change faster. So this kind of work is a computational science problem. It's a data problem, because you deal with massive data sets, you deal with natural language processing, and in the end you're running Python code on a supercomputer. But the goal that you want to achieve is to do this in a better way, such that the next generation of products are integrating this kind of logic. Of course, for the end user this is seamless, but in the back, for the researchers that are developing the algorithm, or the industry people that are applying this to real production code, there's a huge work behind that is then accelerated by running on a supercomputer. Also in the direction of enhanced artificial intelligence, there is a heavy-duty computer science work happening to test new deep neural network models. And on the path to true AI, one thing that is being seen that is feasible to do, but it's extremely complex. Well, it's not possible without a supercomputer first, and it's extremely complex even with a supercomputer, because you have to deal with massive data sources, is not only to do supervised learning or unsupervised learning, but actually to do self-supervised learning, where there's features and annotations that are being extracted by the learning process itself, by the model that is running itself. And it's the vast data source is the way to go, but then you need better tooling, you need better algorithms. So then in the end, of course, you need to apply this to a real problem. So there's multiple work that is happening for that, to enhance the model, to enhance the way you manipulate the data for this model, and also then how to minimize the model that is able still to function correctly, but bring this so that you can have this in the power of your hand on your phone. Another set of examples that I can give you, there is something quite critical for humankind, which is natural disasters. So if you know, in Luxembourg, we've been suffering even in the past years from some very bad flooding. This was seen across Europe. So detecting flooding is quite important. Of course, all the public administrations are doing this kind of work, but there's things that you can do to make this either faster or more accurate. And you can detect floods from different image collections, even from non-classical sources such as social media. People post, "Oh, I had a very bad flood in my backyard," and then they take a picture of it. And because you find the word flood in public sources, and you have a picture of it, and you can detect the geolocation of that, you can see how bad specific flood has actually been for people, which is something that is quite difficult. Of course, if you have a helicopter going around and taking high-resolution pictures, and you're taking high-resolution pictures from satellites as well, all of these data sources can be coupled together to estimate the true damage, the new impact, to create new flood maps, and you can couple data from images, from rain sensors, from across a variety of data sources to do better water management for the future, to see how the bio ecosystem will be impacted, and so to protect the biodiversity that is there. So these things are really a natural place for supercomputers to help, because they have the computational power, they have the storage performance that enable you to look at massive data sets, and also, like I said, they're typically quite well connected to different networks, and you can really bring a lot of data to them in a fast way and do big simulations, modeling, and analytics there. Another example of things that have run on MeluXina regarding climate neutrality and the European Green Deal that you may have heard of. We can take a better use of biomass as a sustainable alternative to fossil fuels. A lot of factories, a lot of facilities that, for example, burn waste wood, but they burn high-quality waste wood, and not secondary products or things that are not of a high quality. But we need to be able to do that well. So then, to do that well, you need to understand how the burning process happens, and then you need specialized tools and specialized knowledge to take advantage of it. And the simulations are very computationally intensive, and that's where a supercomputer helps. In terms of technological leaps, there is something to tell you. The next generation quantum computers, the building blocks, the very basic building blocks for them, are sometimes really being simulated on existing machines with these current supercomputers. But there's also big studies that are happening around physical properties for next generation low power electronics. And of course, we all wish our phone would last more than one day. So for that, you need better power delivery, better taking advantage of the chips that are inside, better energy density. So this kind of work is really happening with the help of supercomputers. And last but not least, personalized medicine. There is a lot of work happening that is going to help for personalized medicine. Sometimes you want to explore how different kind of molecules will behave to specific conditions, and this can help in the drug design process. So you instead of trying this out in a chemistry lab, you are doing this in silico. We are doing this with the help of computation, of simulation and modeling. And to build these data sets, it takes, again, you're running very complex physical and chemical algorithms that take a lot of time. So, and to build this database, you really want to cover many aspects, and this is hugely computationally intensive. Maybe not that much data intensive, but very heavily computationally intensive. And there is a lot of work happening where there's a coupling between traditional simulations and machine learning to make this happen faster. But you still have to start from an existing data set. So the different kind of approaches are being coupled together to make this happen. One thing that I want to talk to you about in brief is a nice project that is coming to MeluXina, which is called Destination Earth, where there's multiple parts of it, and the digital twin part is going to be coming first to MeluXina. We're going to see some work there, where it's a European flagship project. There's a lot of parties that are involved, and a lot of work that will happen in the next decade. In the coming years, there's a part of modeling that will happen. Maybe this is a better slide to show you this, because the European Center for Medium Range Weather Forecast is deeply involved there. So there's two digital twins that will that will be built, and this is with the supercomputers in the loop, because they are the ones that are able to take in the massive data sets and run the equations that are able to help this. And it goes from the better understanding of the past, applying this to the present, but also to the future, and to do real predictions for testing scenarios. That's what we want to see in the future, to see what we can do to influence things, but also to mitigate problems that we're seeing now. So to take immediate actions, and to do things that without a supercomputer is not possible to do. So supercomputers have been doing this for some time, but it really today there's a concretized and a very heavy effort to make this happen. So I would be really happy that when we're speaking in the next years again, I can really show you some of the outcomes of this kind of work that is happening with the help of MeluXina. I think we're gently coming to the session close, but I want to close by showing you a few pictures. There's a few things to show you regarding when the machine was built up. To see that it was a massive effort at the time. There was a lot of work happening to integrate the system, to test the system, and to deploy the system. Thankfully, the system is now there, so all the parts are operating well, and we are having a nice usage, such as the examples that I've been able to show you in the past minutes. If and when you will come to visit MeluXina, this is what you'll see. This is a true picture from the visitor place, where you can see the computational aspects. The MeluXina Mermaid is heavily emphasized on the front end, as well as the Luxembourg skyline. And behind the MeluXina Mermaid, there's a huge team that make it all work, and that bring the solutions to life in terms of expertise, in terms of applications, in terms of operating the machine itself on a daily basis. And if you look from the machine's back, you see also parts that are not only the computational part, but the logic behind, the cloud platform that is behind, the huge connectivity that couples all the bits together, and all of it is working in concert to make things work, not only on the hardware side, but also us at LuxProvide as a team. So without further ado, thank you very much for your kind attention. I hope it was instructive for you, and I'm really looking forward to seeing the kind of questions that you will have.
Thank you, Valentin. It was a mind-blowing presentation for me, and I always learn a lot from these webinars, as I hope our public and our attendees are learning. I really especially loved the real examples that you are working on these days on MeluXina. It always helps, in my opinion, our audience to understand what they could do with such a big machine. So let's see our poll. And I see there is a new question that I invite you to respond to. It's about how do you evaluate the level of information provided during today's session? Was it easy to understand with useful information that was new to you? It was too basic and you already knew everything? Or it was a bit challenging but still got the main points? Last one is if it's too complicated and you struggle to understand. This may help us to understand better if we should adapt our level of understanding on the speeches and everything about the content. Let's see the questions. I see we have some. So one of the attendees is asking if are the previous HPC sessions somewhere available to review? Yes, indeed. And all the HPC Thursday webinar series past webinars are available online on Lux Innovation YouTube channel. And I posted you the link as a response to this question in the question tab. And I invite you to take a look at them and watch them if you missed any. We have another question It says like the following. Is there a possibility to have a small test environment before going to MeluXina? I mean, a sandbox or a smaller version? Thank you. Or is it, yeah, I leave Valentin to that.
Okay, so let me answer that. There is a slide that I didn't show. It's not in my current deck, unfortunately. Our solutions team typically engages with potential users of the machine quite deeply. So what we are doing is we're trying to see where you are and what your needs are, and if you have not had yet the expertise of running in this environment, they will guide you quite deeply and they will propose you a proof of concept. Well, the way we like to call it, it's a proof of value to show what the value that you can get out of the system. So you will start on the machine that you will be running, but the dimension of your proof of concept project will be dimensioned and tailored to you. So we really invite you to come in contact with us, and we will guide you through what is available and how we can help, and to see what you want to do with the machine. And this will lead to a sizing for a small project, but you will be running on the same machine as the biggest code that you can imagine coming out of this Destination Earth project, which is huge in scale. But you will be running on the same machine as them.
So you provide the machine, but you also provide technical support, right? And so all the expertise that really provide is available for customers.
Yes, coming from the application side, from the expertise side, we have people that are helping.
Thank you, Valentin. We have another question. What is the petaflop performance of MeluXina and artificial intelligence performance? And what is the energy consumption?
Okay, so you did not pay attention. This was in my slides. Well, part of it. So this the performance of the machine in the raw performance, aggregated the raw performance is around 18 petaflops. It's a bit above 18 petaflops. This is 18 multiplied by 10 to the power of 15 floating point operations per second in double precision. If you want to run some code on one compute node, on a CPU compute node, then this is of course much smaller, because there's just one tiny brick out of the true full machine. If you want to run on the GPU nodes, a single GPU node can bring you, if I'm not mistaken, around 50 teraflops of performance. The true power of the GPU module, if you want to run on it, is around 15 petaflops just in raw performance. The way we've been able to rank the machine by running a benchmark where you have some efficiency factor, you're never able to run at 100% efficiency whatever you do, but the efficiency there of this module, if you are able to take advantage of almost all of the GPUs at the same time perfectly, was around 10 petaflops, was 10.5 petaflops. So again, 10.5 multiplied by 10 to the power of 15 operations per second. In terms of AI performance, which is not a double precision floating point numbers operations, but reduced precision numbers, then we have almost 500 petaflops of AI performance. So if you're doing deep learning, machine learning, and you're training neural networks, you're running GPT-3 and so on with the help of TensorFlow, or you're running PyTorch code, then you are able to go to larger performance numbers. But it all depends on your use case. Sometimes even heavy-duty computational chemistry or physics applications don't need double precision numbers all of the time. So for some equations, you can run it with lower precision numbers, and that means that you can get more than this 10 or 18 petaflops. So it's really depending on you and your use case. In terms of power, the machine is water cooled for the two computational modules. The two heavy-duty computational modules are around 800 kilowatt if they're used 100% during a single execution. If not, the machine is part of the compute nodes are idle. Of course, they consume much less power because you don't need to. They're not kept at 100% CPU usage if you're not running something on them. So the power consumption is is varying depending on the workload.
Great, thank
So
you.
more or less you could qualify, sorry to complete, more or less you could qualify the machine is a 1 megawatt machine.
Thank you, Valentin, for the complete answer, indeed. I don't see any other questions in our questions tab, and I see we are almost to the end of this session. So I would go, you know already we have a National Competence Center in High Performance Computing here in Luxembourg, and we provide you guidance to understand what is the best service that you need or the best initiative that is available in Luxembourg. We guide you through all the possibilities, and we support you from the business side, from the technical side, and also we provide together with LuxProvide and the university, and we provide training courses, hands-on labs for you to become an independent HPC user. We have also an European outreach to European HPC initiatives available out there that you could take advantage of to solve your problems, to make the best use of HPC infrastructure we have here. So Lux Innovation is your single point of contact. So if you have any questions, you'd like any guidance, you'd like to present what you have in mind or your idea of using HPC, we can help you, and I invite you to contact me for any questions you have. I'm available for setting up a meeting and discussing your personal projects. I again invite you to register to our upcoming event, Supercomputing Day event in Luxembourg at the Chamber of Commerce on the 12th of May. So next Thursday, this is it happening in 1 week. You have a pop-up here to the registration link. So I invite you again to join us for an interesting event where you'll see presentations that may help clear out your doubts and inspire you to make use of HPC and apply supercomputing power to your activities. So I would like to conclude this session. I would like to thank Valentin again for his presentation. It was amazing. I enjoyed it a lot. And I hope to see you next week, all of you from the audience, to our event day at the Chamber of Commerce. Thank you again, and hope to see you soon, maybe for the next edition of our HPC Thursdays. Have a nice day.
Thank you all. Have a nice day.
Bye.
Goodbye.